Okay, so in this problem, it's pretty wordy, right? But don't be intimidated by that. Usually the wordier problems end up breaking down to be quite simple. So let's read through it. Each of the hats shown below has colored marbles placed inside. Hat A contains 5 green marbles. Okay, so 5 green. Oops, let me draw this over here. So I'll write, I'll write 5 green and 4 red marbles. So 5 green and 4 red. B contains 6 blue, so I'll put 6 blue and 5 red. Oops, that's not red. Well, it's red. It's kind of a crimson, but I'm trying to stick with red there. Hat C contains 5 green. Okay, 5 green and 5 blue marbles. Okay. If a student were to randomly pick one marble from each of these 3 hats, determine which hat the student would most likely pick a green marble. Okay, well, we're going to pick then the hat with the most green marbles. There are 2 of those with the most green marbles, hat C and hat A. But in hat A, we have a total of 9 marbles, so the probability of getting a green, right, is 5 out of 9. And in hat C, the probability of getting a green is 5 out of 10, or 1/2. So 1/2 is less than 5/9, right? 4.5 out of 9 would be 1/2. But so hat A is the most likely, and you can compare that by saying 5/8 is greater than 1/2. Excuse me. Okay, determine the fewest number of marbles and the color of these marbles that could be added to each hat, so that the probability of picking a green marble will be 1/2 in each of the 3 hats. It's kind of a fun question, right? So we need this way. If we have 5 green marbles, 10 in total will make a half. So in hat A, I'll add 1 red, right? You don't want to add a green marble here because, and we can't take away marbles, right? If we could take away marbles, that would be nice. But here, we could just add a red to get 10, and it's 5 out of 10. So we'll come back to hat B in the end. It's the most difficult, I think, but it's workable. Hat C, we already have a half, so we don't have to add anything. I'd add 0 marbles, right? It's already at a half. So here, it's an odd number. 6 plus 5 is 11. You want an even number, so let's just add 1 red. So add 1 red, and now we have 12 marbles, right? And you can't add 6 green because 6 green would be half of 12. That's true, but then you'd have 18 marbles, right? So we have to add some green marbles, and then I think what I would do is add some more blue or red marbles to make the amount of green marbles half of the total. So there's lots of ways to do this. I would just pick a round number that feels friendly to you. Let's say if we add, right, we need more than 6 green marbles. Let's say we add 7 green marbles, right? So we have 7 green marbles. Does this work? Well, 7 plus 6 and 6 is 18 is 19. And 7 is not half of 19, so we need to add more green marbles. So we have 6 and 6. That's 12. So if we add 10 green marbles, or 8 green marbles, go one by one to see what's happening here. 8 green marbles plus 12, right? That's 20. And green is 8, it's not yet half of 20, so that doesn't work. Getting closer though. 9 green marbles plus 12 is 21. 9's almost half of 21. Okay. What about 10 green marbles? Well, 10 and 12 is 22. 10's almost half of 22. What about, let's jump up now, 15 green marbles? Well, 15 plus 12 is 27, and 15 is more than half of 27, so we have to go lower. So as you're jumping around here, you can find the limits of where this thing would be. Try 13 green marbles. Well, 13 plus 6 and 6, that's 13 plus 12, or 25. 13 is too large. Try 12, right? And I think you can see why that would make sense. If we had 12 marbles in total, just double that amount, add 12 more, and green will be half of that. So you could jump around like I was doing here, but you might just think again, I'll write this down here. If you had 6 blue plus 5 red plus the 1 red we added, that's 12 in total. So if you need green to be half, right, of the total amount, that means you just double this amount. So if we have 12 plus another 12, we'll get 24. And that means that green, the new 12 we added, will be half. So in other problems, let's say you had, I don't know, 14 marbles to begin with. Well, if you want green to be half, just add another 14 green, right? So that there are a total of 28 and green would always be half. As a shortcut, you can do that. Let's move on. A bag contains 8 green. Oops, can't see that. 8 green marbles, 5 white marbles, and 2 red marbles. Let me just try to color code here. 5 white and 2 red. Can't see that. What is the probability of drawing a red marble? Well, that's just one pick. So you say 8 plus 5 plus 2, right? That's 15. So it's 2 out of 15. Choice 2. There are 2 red marbles in the bag out of the 15 that we have. John is buying tickets for himself at 2 concerts. For the jazz concert, 4 tickets are available in the front row. So let's say this is the stage right here. I actually kind of like to picture these questions here. This is our first row. Let's say it's a kind of curved row at a concert, right? So everyone can see. So 4 tickets are available in the front row. This is at the jazz concert, I think they said. Okay, so let's say 1, 2, 3, 4. All right, and 32 tickets are available on other rows. So 32 tickets in, I'll draw this as other rows. In other rows. So you're gonna picture in total there's like these 36 tickets available in this whole jazz auditorium. And I would write that down. Keep track of this. 36 tickets. All right. In the orchestra concert, so orchestra is over here. This is the orchestra stage. Let's say a different concert. It's the orchestra. Okay. 3 tickets are available in the front row. So you have this row right here, and there's the seats, right? And there are 1, 2, 3 seats available. So 1, 2, 3 seats. And 23 tickets in the other rows. So 23 tickets in other rows. And bear with me here because really, I think when you're solving these problems, it's important to picture what's going on. So here there are 26 tickets in total. Okay, what's our question? John is randomly assigned one ticket per concert. Determine the concert for which he's more likely to get a front row ticket. Oh, all right, so we're just comparing these two. So in this one, it's 4 out of 36, right? In the jazz concert, 4 out of 36. And if you reduce that, that's 1/9, right? In the other concert, what is it? Well, there's 3 out of 26. Okay, well, 3 out of 26 is 3 going to 26. No, it's not reducible. So you have to compare 3 over 26 and 1/9. How do we do that? Well, here it's just comparing a proportion. So there are many strategies for this. I'll write this up here. 1/9, if I multiply it by 3 over 3, what do we get? We get 3 27ths, right? And in the other, so it's 3 out of 27. That's your chance of getting a front row ticket here in the jazz concert versus 3 out of 26. So which one's greater? Well, think about the pieces of a fraction. Here we have 27ths. It's like taking something and cutting it in 27 small pieces. Whereas in the other case, you have 26ths. Take the same pizza or whatever, instead of cutting it in 27, cut it in 26. What's going to be larger? Well, the 26 slices will be larger. So it's better to have 3 out of 26 than it is 3 out of 27 because there's more to share, right? There's smaller pieces. So 3 out of 26 is certainly the higher chance. And then at the orchestra, it's more likely you'll get a seat in the front row. Even though there are more seats available in the front row of the jazz concert, there are more in total. You're just comparing those two proportions. All right. Okay, so in this problem, we're allowed to use 3 digits, 0 through 9, followed by 3 letters from an alphabet having 26 letters. If repetitions of digits is allowed, but repetitions of letters is not allowed, determine the number of passwords to be made. So repetitions of digits, we have 10 digits to choose from, 0 through 9. Don't forget to count 0. So it's 10, we can choose any 10 digits once and then twice. So for each of the 10 ways we can pick the first digit, there are 10 ways to pick the second, and then 10 ways to pick the third. And then for the alphabet, we can't repeat those letters. So there are 26 letters to pick from, then 25 because we can't repeat, and then 24. So here, there's going to be a lot of ways to make this combination. We have 10 to the third, which of course is 1,000, times 26 times 25 times 24. In total, right, we have 1,560, 15,600,000, quite amazing, of course, ways to arrange these digits into a password. And then the next one says, if repetition is not allowed for digits or letters, how many fewer passwords can be made? Well, instead of 10 times 10 times 10, we can first choose from 10 digits. For each of those 10 digits, there will now be 9 other choices because we can't repeat any of the digits that we start with. And then, for each of those 9, there will be 8 left to pick from. And that's it, 10 times 9 times 8. And then again, 26 times 25 times 24, and they want us to compare these two numbers. So we have 10 times 9 times 8 times 26 times 25 times 24, right? We have 11,232,000. And we can quickly just pull up our previous entry to subtract. I'm just going to type it in now. 15,600,000 minus 11,232,000. Okay, we have 4,368,000. Quite a bit more. So if you had a large company you're looking at here, you'd definitely pick the more combinations. The more combinations, the safer the password. So I would go for this one with repetition. Okay. Maria has 10 index cards labeled 0 through 9. She puts them in a bag, selects one at random. The outcome that is most likely is which of the following. So odd numbers, well, the probability that we get an odd, right, what could you get? You can get 1, 2, 3, right, 5, oops, I'm saying, oh my gosh, 2. Oh boy, long day. 1, 3, 5, 2, of course, is not odd. 7, 9. So there are 5 to choose from out of, right? Out of what? Out of 10. Oops, because we have 10 cards. Okay, so in this problem, Maria has a set of 10 index cards labeled with the digits 0 through 9. So I picture there are actually just 10 cards, right? And the way I picture this question is that on each card is a single digit, 2, 3, 4, 5, 6, 7, 8, 9, 10. So on each card is a single digit, 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 cards in total. And they're saying what's the most likely? The probability of getting an odd number, which is what? Well, we have 1 odd, 2, 3, 4, 5 odds out of 10, or 1/2. Okay. The probability of getting a prime number is what? Well, 1 is not prime, but 2 is prime. So 1 prime, 3 is prime, 2, 3, 4. So it's 4 out of 10, less likely. So we're trying to find the most likely, so that one's got. A number that is at most 5. So 0, 1, 2, 3, 4, 5. So the probability that the number x is at most 5, so less than or equal to 5, is equal to 6 out of 10. So far that's the most likely, so 1's gone. A number that is divisible by 3. Well, 3 is divisible by 3, 6 is divisible by 3, and so is 9. That's 3 out of 10. The most likely is choice number 3. Okay, so this person's buying all this candy. You have 6 chocolate pieces, 4 fruit-flavored pieces, right? So 6 chocolate, 4 fruit-flavored pieces, and 2 mint. He selects 3 pieces of candy at random without replacement, so you don't put the candy back. Calculate the probability that the first piece will be fruit-flavored and the other 2 will be mint. So just break this in pieces. The probability that you will get a fruit, right, and then a mint, and then a mint after that. So it's the probability of getting a fruit times the probability of getting your mint times the probability of getting a mint after that. The first time the probability of getting a fruit is what? Well, it's 4 out of the total, which is just what? 4, 6, 2, so 12. So 4 out of 12, or 1/3, just that, of getting a fruit, times the probability of getting a mint, which is 2 out of what remains. So there were 12 to begin with, now there would be 11. Times, well, if you got a mint the second time, there's only 1 mint left out of 10. So we can reduce this a little bit. 2 over 10 is 1/5, and we get a third times an 11th, a 33rd, times a fifth is 150 plus 15, so it's 1 over 165. Not very likely, right? Lots of combinations. Next, they ask us, what's the probability that all 3 pieces will be the same? Okay, well, we can get 3 chocolate, so we want to find that probability, or we can get 3 fruit. We can't get 3 mints because there are only 2 mints to begin with. So what's the probability of getting all chocolate? Well, that's a third the first time, and then there would be, sorry, not a third. There are 6 chocolate out of 12, so it's a half. But then the second time you have to get chocolate, there will only be 5, not out of 12 this time, but out of 11. And the third time there would be 4 out of 10. Or you can get 3 fruits in a row. The first time there's a third of candy that's a fruit, times this is the second time, second way to times getting fruit the second time. The chance of that happening, well, now there's 11 candies, and there are not 4 fruits, but 3. And the last time there would be 2 out of 10. So these reduce nicely. These 3's cancel out. 2 over 10, that's 1/5. So that's 1/5 times 1 over 11, or 1/55th of a chance of getting 3 fruits in a row. Here, 2 and 4 is 2, 5 and 10 is a half, and 2 and 2 is 1, so there's 1/11th chance. 11th plus a 55th. Well, 11th, we can think of that as 5 over 55, plus 1 over 55. Finally, we get 6 over 55 for that one as well. So really all you're doing in each case is saying, okay, well, what's the probability of something happening? Well, how many, what's the chance of that actually happening to begin with? Well, here we just found that probably getting 3 chocolates in a row. So assume it happens. How likely would that be to happen? And then 3 fruits in a row, and then go from there. We add these two because they're 2 separate events. Either you're going to get 3 chocolates or 3 fruit candies. You're not going to get 3 of both, right? Because you're not going to keep picking over and over again. All right, thanks.